So we said before that free energy and equilibrium are connected and they're saying the same thing. In this section, the second bite in our free energy and equilibrium series, we're going to calculate delta G under non-standard conditions. See how that affects, how changing concentration and temperature affects delta G, and apply that to some biochemical systems. So we said before, we talked about that the little degree sign means standard conditions, whereas not the degree sign means not standard conditions. So standard thermodynamic conditions are conventions that we've all agreed on in order to make comparisons. So those conventions are everything is pure, 1 molar for all solutions, 1 atmosphere for all pressures, and usually a standard temperature of 25 degrees C. Now, sometimes those conditions are actually really hard to achieve for a real system, and so we kind of estimate or calculate what it would be like under those conditions. Those might not be the conditions that we care about. In a real reaction mixture, we don't necessarily start with 1 atmosphere of each of the components or 1 molar, and perhaps we're not interested in 25 degrees C. So, how do we determine what delta G is going to be under those non-standard conditions when what we know about are the standard conditions? We have an equation for that. Delta G equals delta G under standard conditions plus RT ln Q. So Q is the same Q from back in equilibrium. Q helps us predict the direction of the reaction, the way it will go to get to equilibrium, the same way that delta G does. And so it makes sense that they are mathematically related. Put another way, we said that the reaction can be spontaneous in either direction, and it depends on what you're starting with. So, for example, we see in these figures from your book that in the first figure over here, we see that this reaction proceeds, that the equilibrium is more toward the products. So if your Q starts out with mostly reactants, then you're going to find that it's going to proceed toward the products. And here, if you start over here and you have too many products, you're going to proceed toward the reactants. That the delta G standard is referring to the energy difference between the reactants and the products. Okay, and since the reaction is more toward the products at equilibrium, we'll see that that'll give us a negative delta G standard. So if you had equal amounts, you would go toward the products to get to equilibrium. The same way here, if we had equal amounts of reactants and products, equilibrium is more toward the reactants, so the delta G standard of this reaction is going to be toward the reactants. It's going to be non-spontaneous in the forward direction. And we see here that since the equilibrium is with equal amounts of reactants and products, that if you started under standard conditions with equal amounts of reactants and products, you would be at equilibrium. Your reaction wouldn't spontaneously go either forward or reverse. So, reactions proceed toward equilibrium where free energy is lowest. They may proceed toward reactants or toward products to get to equilibrium. And spontaneity really refers to the portion of the reaction in which the free energy decreases from the starting mixture to the equilibrium mixture. Okay, so we can see how concentration is going to affect delta G. So here is an important reaction. N2 plus H2 becomes ammonia. We've talked about this one before. And here we know that delta G for this reaction is negative 33 kilojoules. And we can see 3 different initial concentrations for our reaction mixture. And so we can see how delta G changes with these different concentrations. In each case here, we're going to use delta G equals delta G under standard conditions plus RT ln Q. And here, Q is going to be, so delta G plus RT, And Q is going to follow the same pattern that it has the entire class. So Q is going to be the pressure of the products here, NH3, raised to the coefficient squared, divided by the pressure of the reactants. So pressure of N2 times the pressure of H2 cubed. All right, so if we do one example of this, we'll see that if we take the first set of conditions, we've got 1 atmosphere of N2 and H2, the reactants, and only 0.02 atmospheres of the products. So we have much more reactants than we have products in this case. Okay, so delta G standard here is negative 33 kilojoules. And then we're going to plug in RT. So R, which value of R do we need? We need the one with the joules, but we're going to convert it to kilojoules here. So 8.314 times 10 to the minus 3 kilojoules per mole Kelvin. The temperature we said is going to be, it needs to be in Kelvin, but we'll take 298, just keep that the same. And then ln of Q, so we're going to plug in our values that we have above. So 0.020 atmospheres squared divided by 1 atmosphere times 3 atmospheres cubed. Okay, so if we do the math on that, we see that delta G equals negative 606 kilojoules. If we do the same thing, but for the second set of parameters, where here we have N2 and H2, the reactants are really low, and NH2, the product, is really high. If we do that, we get that delta G equals positive 7.9 kilojoules. Okay, and so that's when Q is 1 atmosphere squared, or sorry, it was 2 atmospheres squared divided by 0.01 times 0.03 cubed. Okay, and then if we do the third set of conditions, where we have everything is 1 squared divided by 1 times 1 cubed, then we get ln of 1 is 0, so we get negative 33 kilojoules. Okay, so let's talk about this. What does this mean? So the third case, this is standard conditions. So if you have equal amounts of all of your reactants and products, this reaction will proceed spontaneously in the forward direction to get to equilibrium. If you have a whole bunch of reactants and only a little bit of products, then the reaction will be even more spontaneous in the forward direction because it has sort of even further to go to get to equilibrium. However, that's like the first case. However, if you take the second case where we have a lot of products and very little reactants, you see that the direction of the reaction changes. That if you have a whole lot of products, the reaction actually has to proceed in the reverse direction. It has a positive delta G, albeit a small one, in order to get to equilibrium. Okay, so that's what the standard conditions means, and we can see that changing the conditions is going to change the spontaneous direction of the reaction. It turns out that biology puts this to work. One of the most important reactions in your glycolysis metabolism is the reaction of something called glucose 6-phosphate to fructose 6-phosphate. So this is part of how your body uses the food that you eat. And it turns out that this reaction has a positive standard delta G. It's not spontaneous under standard conditions in the forward direction. And yet your body does it all the time. So let's calculate delta G when we have the typical cell conditions. So in a typical cell, the glucose 6-phosphate concentration is 120 micromolar, and the fructose 6-phosphate concentration is 28 micromolar. And we're going to assume that temperature is 37 degrees, or biological temperature. Okay, so we can calculate delta G under these conditions using the standard delta G plus RT ln Q. Okay, and so standard delta G is positive 1.7 kilojoules. Okay, plus R is 8.314 times 10 to the minus 3 kilojoules per mole times Kelvin. T, we said, is 37 degrees Celsius, which is 310 Kelvin. And ln of Q, so this is going to be products over reactants, so we'll take 28 micromolar divided by 120 micromolar. And we can leave these in their micromolar things because the units will cancel out. Okay, so if we do all of that, I get that delta G under these conditions is 2.1 kilojoules. So biology uses the fact that biology manipulates this reaction so that we always have a lot more of the reactants, glucose 6-phosphate, than we have of the products, fructose 6-phosphate. And by doing that, biology makes this reaction be spontaneous in the forward direction. Okay, so we have talked about how you can change the concentrations in order to manipulate which direction is the spontaneous direction. And a reminder that standard thermodynamic conditions are 1 molar and 1 atmosphere and 25 degrees C. So get some practice, ask me questions.